Hello, ladies and gentlemen, and welcome to this next in this year's series of educational webinars on material characterization entitled Basics of Oscillatory Rheology. Before we commence with the webinar, which will last for 1 hour, I would like to draw your attention to the Q&A text entry box at the bottom of the screen. We encourage you to type questions you may have at any time during the presentation so that these can be answered at the end during our general Q&A session. This webinar is being recorded and you will be sent a link to the recorded presentation once this has been prepared for publication. The presentation itself will also be made available to you for viewing in the near future. So without further delay, I would now like to hand over to the presenter, Jan-Philipp Ploog, Group Leader Rheology Applications, who will be your moderator for this webinar.
Thank you very much for the introduction, Klaus, and good morning and welcome everybody also from my side. Today's webinar will be a more basic one compared to the others we did so far this year. This webinar I'm going to talk about viscoelasticity and how to determine quantitatively how viscoelastic your sample is. We're going to talk about creep and oscillatory rheology. And before we're going to jump into the webinar, let me just run you quickly here through the agenda. After I'm going to repeat some basic terms of rheology. For those of you maybe more familiar just with the rotational part of the business in terms of viscosity, I'm going to talk about briefly viscoelastic behavior. Where does it come from? What does it mean for your products? Before I'm going to talk about the experimental approach to viscoelasticity, namely creep and recovery. So always when you want to mimic small stresses like gravitational sag, for instance, when you are interested in leveling sagging behavior for coatings or some food coatings whatsoever. But more importantly, the focus will be on oscillation. I'm going to talk about the amplitude sweep. What do you have to do? How is it being conducted? What is the information you get in terms of linear viscoelastic regime, but also yield stress? The main topic of today's lecture is going to be the frequency sweep. So this is going to be the goal for us today. We want to understand what we need to do to determine not just the viscoelastic behavior, but the speed-dependent viscoelastic behavior. Again, always keep in mind that everything I'm talking about here today is meant for you to mimic the reality that you have to face best, meaning that we don't want to measure just something in rheology on our rheometers, but we want to mimic a certain product's behavior towards a certain application or processing step. And those are always speed related. So the frequency sweep is going to be the main topic of this lecture. Afterwards, I'm going to shortly talk about what else can be done in oscillation, namely temperature and time sweeps, for instance. And then I want to close this presentation with talking about the time temperature superposition principle, what you can also do with oscillation to enhance the range of specific speeds that you can achieve on a rheometer, and to close the loop towards the basic viscosity. I'm going to talk about Cox-Mertz rule, okay, and how the shear viscosity and the complex viscosity that you measure in oscillation can be compared to each other. All right, let's just jump into the basic terms again. Might be a good starting point for some of you. When people start to approach rheology, the first parameter they usually think about is the viscosity. What is the viscosity? The viscosity, as you see in here, defined by Newton's first law of flow, is nothing else but the ratio between the shear stress and the shear rate. It's thus just a constant of proportionality between those two factors. Always keep in mind that viscosity is never measured directly by any given measuring machine, a rheometer, viscometer, whatsoever. It's always calculated according to those two parameters. Where do those parameters come from? Let's have a quick glance here at the basic two-plate model again. That might be familiar to some of you. When you have a fluid confined between a stationary and a movable plate, can be the rheometer, can be some kind of other flow field that your product sees in its life cycle. You can apply a certain force on the movable plate, okay, and this will form a laminar flow field. You have different fluid layers that flow on top of each other, okay. The force with which we pull on that plate is then called the shear stress. As you can see, it's nothing else but a pretty one-dimensional pressure tensor, pretty much, that acts only in the flow direction, as it is more or less just a pressure. The SI unit for shear stress is Pascal. Okay, I know I talk to a lot of people right now that work in the United States, so you might not be familiar with the SI term. Pascals for you would be something like dynes per square inch or dynes per square centimeter or so. The deformation that I'm going to talk about later on when we go into oscillation is a parameter that just describes a displacement over the distance. So we call it deformation. Some people call it strain. Okay. The problem with a deformation is that it is in a laminar flow field like this, not constant. Okay, the deformation is at max at the movable plate. It is 0 at the stationary plate, and thus for steady shear flow experiments, we need to find another parameter that describes just the dynamic state of the whole fluid, and that parameter is the shear rate. For those of you that might be familiar with it, the shear rate is nothing else but the deformation or speed gradient in this flow field. Okay, so the speed difference between those two fluid layers here is the same as between those. The shear rate thus is constant over the whole gap. For now, however, we should keep in mind those two parameters, deformation and stress, because we're going to talk about them more excessively later on during the presentation. We do have other webinars more on the rotational side of the rheology business. However, I don't want to dig any deeper into that. The problem with rotational tests, however, is especially when you use coaxial cylinder geometries and viscometers or rheometers, is that you have no means of actually quantitatively measuring the viscoelastic response of your sample. You only measure the viscous response in terms of viscosity, yield, and so on. Where does this viscoelastic response actually come from in your product? The main reason behind elasticity is structure. It is that easy. As soon as you have a structured fluid, can be a polymer solution or polymer melt, where the structure comes from the entanglements between the single polymer chains, can be some kind of three-dimensional network found in emulsions or suspensions, either being droplet clusters or solid particles held together by van der Waals forces. As soon as you have structure, can be this or that, can be a wild mix of those. This structure enables your fluid to absorb energy elastically while you deform it. Okay, you chew a chewing gum, you deform the chewing gum while you do so, and this deformation energy is stored elastically right in the polymer chains, okay, in your product. What's going to happen then is that after the deformation process, that energy is then used for back deformation, or we call it relaxation, okay, which for a chewing gum is something that you want to happen, because otherwise it would not be a chewing gum. When you have, for instance, something like a shower gel or so, which behaves too elastic because your polymer might be of too high molecular weight, your end customer, be it the processing people that have to fill that stuff into bottles, or the actual customer that buys your product in the grocery store, will feel that elasticity. Okay, in the filling process, when your shampoo is too elastic, you will see stringiness. Okay, the same will happen when an end customer is actually applying your product. When the system behaves too elastic, you will strands that form when the customer takes his hand off his arm, for instance, after rubbing in the shower gel, and that gives the customer a sticky sensation. Okay, in that regard, you do not want elasticity. Okay, as a rule of thumb, you usually never want elasticity. Elasticity is usually always bad. When you spray a coating, the misting behavior will not be good. When you have maybe a curtain coat that is too elastic, you will have an uneven surface. You have a too elastic polymer melt at a certain characteristic speed in the extruder. You will have dye swell behavior. You will have shark skin. You have a food product that is too elastic. It will feel slimy, or you will have problems to swallow it. So no matter what kind of products you are researching on, elasticity is always something bad, usually. And that is the reason why we need to understand the elastic response of our products. And that is why we have to quantitatively measure it. Okay? And this can be done, just one basic slide here in terms of where this elasticity actually comes from. I talked about the rubber band already. The elasticity that we're going to quantitatively describe via our logical methods derives from pretty much the principle Hooke's law or spring law. Okay, meaning nothing else that when you apply a force to an elastic body, here is spring, you will achieve actually a certain amount of deformation. And the amount of deformation that you can achieve pretty much depends just on the spring constant, okay, of your spring. The higher the spring constant is, the lower the amount of deformation will be that you achieve when you apply a certain force. When we transfer that to our let's say Newton's law of flow, to go into more the viscoelasticity, we find that again a certain stress or force will result in a certain deformation for your viscoelastic body. But now we don't call the constant of proportionality in between the spring constant anymore. We call it modulus, okay? The complex modulus G star, okay? However, you will see later on this complex modulus incorporates not just the elastic components of your viscoelastic fluid, but also the viscous components of your fluid. And I will show you how easy it is that we can separate them into viscous part and elastic part, but more on that later. Okay. So the question is, how can we model those? I don't want to go into too much detail here, but when we talk about creep recovery, we dig into that slightly deeper here. When we model purely viscous behavior, you usually use the dashpot. Okay, dashpot behavior means you put force, you put stress into a certain fluid, okay, and this fluid will run away with a certain speed, as fast as it can. And the speed with which it can do that, or the speed with which you can actually push the stamp into the fluid with a certain force, depends solely on the viscosity. Okay, nothing else. All the energy that you put into the system is what we call dissipated by viscous flow. Then on the other hand of the spectrum, we have the purely elastic spring. We talked about that. Hooke's law, you put force on your elastic body, it will be extended to a certain extent, and the extent depends purely on the spring constant. Okay, in our case, we'll talk about this a little bit later on, modulus. Okay, and then we have the real world, the in-between world, viscous and elastic components thrown together. Again, I don't want to go into detail. We have Maxwell or Kelvin models to model that. But in creep recovery in a second, we're going to talk about the Burgers model, because it combines pure elastic and purely viscous behavior with the viscoelastic intermediate. But I don't want to go into constitutive equations right now, so don't be afraid. So now that we know that there's viscous and elastic components to your fluids, how can we measure them? And the first experimental approach I want to talk about is creep and recovery. It was the first experimental approach actually to quantify between elastic and viscous components in your fluids. However, and I'm going to talk about this in a second here again, it's a test used nowadays mainly to mimic how a certain product behaves towards very small stresses. So it's mainly a test to mimic how something reacts towards gravitational sag. Okay. What is a creep and recovery test? You apply an instantaneous shear stress jump and monitor how your system reacts towards that. The advantages are that it is a non-destructive method because we work in the linear viscoelastic regime at small stresses. More on that later. We can distinguish quantitatively between elastic and viscous properties, and of course we can determine time-dependent reactions to such changes. However, and again I want to stress that you will get no speed-relevant information out of that test. However, let's have a look at the test anyway. How would it look like? For instance, to make it easier for you, for those of you who might not be familiar with it, how does it look like for a purely viscous sample? For a purely viscous sample, the moment you apply the stress jump, okay, the pedal will start to move into the fluid here, okay, in talking model. The deformation that you monitor, okay, will go up with a constant slope. We call that viscous flow regime. Okay, as soon as you release the stress, the deformation will stay at a constant level. All the energy was dissipated by viscous flow. All the deformation is irreversibly lost. There is no structure in your fluid that can actually store some of the energy to use it for back relaxation. Okay, talking on the rheometer, your rotor wouldn't move here. Then the rotor starts to move clockwise, for instance, and when you release the stress, the rotor stays exactly where it is. Nothing happens to it. This changes dramatically when we look at how a purely elastic sample behaves here. Okay, same test, we apply the stress jump, and what we see is that the deformation jumps up, okay, instantaneously, stays at a constant level, and as soon as you release the stress, the deformation also goes back to zero. Okay, the deformation is completely reversible. Okay, all the applied energy in the stress jump is stored and then used for back relaxation. Okay, when we look at the rheometer for a purely elastic fluid, okay, the rotor moves instantaneously into a certain position, stays there, and then when you release the stress, it's being pulled back to its initial position was in before we started the test. Okay. Now when we look into the real world again, and we have a viscoelastic fluid, creep and recovery looks slightly different, of course. Just a mix between those. What you're going to see is that first of all, the purely elastic component of your fluid is excited. Then you go through the transition viscoelastic element here at 2, and then under 3 you go into the purely viscous flow regime. You release the stress, the spring or your elastic component is relaxing instantaneously, then some of the energy is used for back relaxation from the viscoelastic element here at 2, and nothing is being recovered from the purely viscous element. Meaning from this test you get an absolute measure for how much elasticity or how elastic your system reacted towards that stress and how viscous your system reacted towards that stress. Okay, and that information you can then use to custom tailor a certain formulation towards a certain application. However, again, most of the applications that you want to mimic with a test like that are gravity-driven processes, leveling, sagging behavior. However, this is not all a creep and recovery test brings you. It is still excessively used in some industries to also determine the zero shear viscosity. Okay, imagine you have a enormously highly concentrated xanthan gum solution, for instance. Okay, one of the worst case scenarios in terms of shear thinning behavior. You can go as low in shear rate as you want to, you will still observe shear thinning. You will not be able to reach the Newtonian plateau, the zero shear viscosity. So what a lot of people do is they do a creep and recovery test, and now just by calculating the zero shear rate via the slope in the viscous flow regime, and by the stress that you apply, you can calculate the zero shear viscosity. Okay, for extremely shear thinning fluids, that is a huge advantage actually, and it's a very quick approach also. You get information on the equilibrium deformation and on the recoverable deformation. We talked about that though, what is the viscous and the elastic component of your fluid towards that stress. You can get a retardation time from a creep and recovery test, meaning nothing else but how long does your fluid need to actually come to rest again, to its motional equilibrium, okay, after you stressed it. And you already get an information about the amount, the absolute amount of elasticity via the elastic modulus that you can calculate just from the zero level. From the zero level deformation and the stress that you applied. However, this elastic modulus gives you only the information on how elastic does my system react towards very small stresses. Again, don't forget we work at very, very small stresses here. So I want to stress that again. Gravity-driven flow fields, okay, no matter if it's like a slump test that you want to do with construction materials, or if you want to model how a coating will actually level or sag on a specific substrate, this would be the test to go. We do not get any speed-specific information from this. Okay, for this we need oscillation, which is the state-of-the-art approach to viscoelasticity. When we do oscillatory tests, it looks very much like this, and we look at the two-plate model again, that you don't work in a steady motion, one directional, but that you oscillate on your sample back and forth, back and forth. And now we have pretty much two sets of parameters that we can play with. One is the strain itself, or the deformation itself. How far do I want to go? Okay. To determine the stress level we want to put our system under. And that's the huge advantage in oscillation, we can, I hope you saw that the animation looks better on real PowerPoint. We can of course play with the speed. Okay, we can play with the characteristic speed that we apply, and of course temperature and others. But the two main parameters are strain and stress, amplitude, and speed. Okay, here just as a graphical depiction, how does that look like? You apply a sinusoidally modulated strain or stress amplitude to your sample, and you monitor what's going to happen. Okay, on your rheometer, you see that the rotor is going to move back and forth, or sometimes you won't see that. Don't be surprised if you don't, because we work at so small deformation, sometimes at so small strains that your eye will not be able to resolve the motion anymore. Sometimes this rotor just goes back, let's say 50 to 100 nanometers, okay, and you will not be able to see that anymore. So what does happen then in your sample? What do we measure? Okay, and for that, let's have a look at the extreme cases again. For instance, you have a purely elastic body. When you have a purely elastic body, and you, for instance, apply as I told you before, a sinusoidally modulated stress amplitude here in red, your elastic body will follow directly, Okay, you start the motion. Think of the creep test again. You apply a stress. Your elastic body will follow that stress instantaneously, meaning that the input signal stress and the result or the output that you actually measure, the deformation, are 100% in phase. Your phase angle or phase shift angle delta is 0. Okay, meaning nothing else. You put in a sine wave, you get out a sine wave. Okay. Now let's have a look at the other extreme. When you have a purely viscous fluid, okay, we do the same thing. We apply a sinusoidally modulated stress amplitude here in red. However, the viscous fluid or the viscous body will not follow the input stress instantaneously. It will follow the input signal with a phase shift of exactly 90 degrees. Meaning nothing else that you put in a sine wave, you get out a cosine. Okay, and this becomes very important a little bit later on when we're going to talk about separating the modulus into a viscous and an elastic component. Okay, keep that in mind. However, again, in reality, we are somewhere in between. We have viscoelastic fluids, some viscous components to it, some elastic components to it. And when you do the same test, this phase shift, the phase angle will thus be somewhere in between pure elastic behavior and pure viscous behavior. Okay, this is what you measure. So let's not talk about wave math too much here. In terms, I also don't want to run out of the agenda here too much. But what I told you is that this complex modulus, okay, that we measure as the constant of proportionality, again, between stress and strain, can now be separated into two parts. Okay, the first part being the G prime, the so-called storage modulus or elastic modulus, and the other one, the complex part, and again I don't want to go into complex numbers today too much, is the G double prime, which is the loss modulus, the viscous modulus. Some people also call it the damping. Okay, and all that depends on the phase angle we have to take into account. Here in this graphical depiction, when the phase angle goes to 90 degrees, okay, your G star, your complex modulus, becomes just G double prime, purely viscous behavior. Okay, when your delta becomes 0, okay, your complex modulus becomes the G prime, the elastic modulus. Okay. However, of course, we are smart enough to separate the response of the fluid that we investigate into one part that oscillates without any phase shift. We call that the elastic component. We call that the G prime. And we separate it into one part that oscillates directly 90 degrees phase shifted, and we call that part the loss modulus or viscous modulus. Okay, and thus we have information on how viscous and how elastic your system reacts. And I told you before, we look into more detail in a second. Now we have the luxury that we can do that as a function of characteristic speed. What else do we get from an oscillatory test? Phase angle we talked about. We also get the loss factor, okay, the so-called tangents delta value, which is nothing else but the ratio between G double prime and G prime, because why that is important I'm going to talk about a little bit later. We also get a viscosity function of an oscillatory test, the complex viscosity, eta star, which is nothing else but the complex modulus divided by the angular velocity, or the angular velocity or angular frequency. And how that compares to the shear viscosity I'm going to talk about later on when we talk about Cox merits. And as I said, very, very important, we get a measure for this characteristic speed. The angular frequency or angular velocity, omega, which is nothing else but 2 pi times the frequency that you work at, gives you a direct correlation to shear rate. Okay. So when we do an oscillatory test, we have to start with the amplitude sweep. With the amplitude sweep, we stepwise increase the amplitude in either stress or strain. Okay. Again, depends on how you want to approach your sample. CS always stands for controlled stress, CD always for controlled deformation, and we keep the frequency constant, and we determine the area where my material functions are independent of the stress or deformation applied. And the area where they are independent, we call it linear viscoelastic range. I'm going to show you an example here in a second. And another beauty of the amplitude sweep is that as we determine the linear viscoelastic range, we usually also determine the end of this linear viscoelastic range when your behavior or when the behavior of your product becomes nonlinear. And this tells us when our structure breaks down. So a lot of people use this test also determine a yield stress in their products. How does that look like now? As I said, here just a graphical depiction of what we're going to do. We stepwise increase the stress or strain amplitude while we keep the frequency constant. Okay. And now when we do that, let's just monitor G prime now. You're gonna, for every kind of sample, you're gonna find a behavior like this, that you have an area where the modulus itself is no function of the applied stress, and we call this linear viscoelastic. And then at one point or another, speed dependent, I'm going to talk about this in a second, this linear regime is left. Okay, the modulus becomes a function of the applied stress, and we call that nonlinear behavior. As soon as this nonlinear behavior starts, the structure in your fluid is being destroyed. Okay, and as we want to work on the intact structure, we want to work in the linear regime. So this is a pre-test that all of you have to do when they do oscillatory rheology. What is interesting, what you see here, is that the length, okay, of the linear viscoelastic regime is speed dependent. The higher you choose the characteristic speed that you work at, you will see the longer the linear viscoelastic regime becomes. And this is just a question of time scales. Okay. The higher the speed is that you work at, the smaller the time scale is that you give your system for relaxation. High speed, as time scale is nothing else but the inverse of the speed. High speed equals small time scale. Low speed equals large time scale. Okay. The smaller the time scale is that you give your system for relaxation, the more elastic it will behave. And you see that in the frequency sweep a little bit later on. The faster you stress your sample, the earlier it will start to just sit down and say, no, I cannot follow this motion anymore. I will behave like a solid body now. And the more solid-like, the more elastic it will behave, the longer the linear viscoelastic regime is. So when you want to do a frequency sweep afterwards in a certain range of frequencies, always do this amplitude sweep at the lowest frequency that you want to work at, because you know when your system behaves linear at that speed, it will always behave linear at the higher speeds. Okay. This dependence, interestingly enough, is larger for the stress dependence than it is for the deformation dependence. So with that information now, that we know where the linear viscoelastic regime is for your sample, you can actually go into the frequency test. The test that is the goal of our, let's say, viscoelastic analysis that we actually get information on how viscous and how elastic your system will react towards a very characteristic speed that then correlates with your process, with your application that you're interested in. So we do vary the frequency now. We keep stress and deformation amplitude constant in the linear viscoelastic regime. We want to determine the material structure as a function of speed, something that we usually cannot do in rotation. In principle, we can measure the elastic response in rotation when you have a rheometer that is capable of normal force measurements. However, for most viscoelastic fluids, polymer solutions, polymer melts, whatsoever, you will not be able to measure in rotation because of the effect that we call Weissenberg effect. That when you shear your sample, okay, in the gap on the rheometer, the sample will leave the measuring gap at one point or another, usually very, very early, because your sample does not want to be stressed. Okay, always keep that in mind. Your sample does not want to be stressed. It tries to escape the stress level, and the only way the sample can is by leaving the gap. We call that Weissenberg effect. Okay, so this is why we do oscillatory measurements. Here, the graphical depiction on what we do. We're going to stepwise increase or decrease the frequency, and we do that at constant deformation or stress level. Okay. Now, how do your products react towards something like that? Let's look at the extreme cases again once more. Let's have a look at the purely viscous behavior first. For a purely viscous fluid, no matter what characteristic speed you apply, the viscous behavior will always compensate the elastic behavior. G double prime will always be above G prime. However, as we have for ideal viscous samples, a slope of 2 for G prime and a slope of 1 for G double prime, it's a no-brainer that those will at one point or another show a crossover. Okay, which is kind of surprising. Because you might think, why should a purely viscous body show an elastic response? Again, we talk time scales. Okay, so when you oscillate too fast on pure water, even the water molecule is not able, or the water clusters, let's say, are not able to follow the motion anymore. Okay, they will stand still. Water will pretend that it's ice, and we call that dynamic glass transition. Okay, but this is only reached at extremely high speeds for a purely viscous body. Okay, a purely elastic body looks different, of course. For a purely elastic body, or a more or less elastic sample, let's say, like a cross-linked polymer, like a real gel structure, a real physical network, the G prime, the elastic modulus, will always overcompensate the G double prime, the viscous modulus. However, the important information from something like that, when you look into gels, for instance, is G prime, that gives you the gel strength itself, and it will also give you the possibility to calculate the mesh size, the network configuration of your gel. But in addition to that, the G double prime gives you information on how brittle, on how deformable your network is. Remember, G double prime divided by G prime is this tangents delta value. For a given network, tangents delta gives you the, let's say, brittleness information. Let's just say you are in polymers, you use a specific polystyrene to make auto parts, let's say bumpers, for a car. Okay, you can have two polystyrenes that have the exact same G prime in the solid body. Okay, but they have different G double primes. The one with the lower G double prime, meaning the lower tangents delta, will be the stiffer system, not so deformable, meaning that when it breaks, it will fracture not so nicely. You have a lot of splinters flying around. Okay, the better deformable, the better damped polystyrene, for instance, would be the much better material to formulate a bumper material, for instance. However, those were the two extremes. Let's have a look at viscoelastic response. Okay, and here you see what I was talking about earlier when we talked about time scale. Every viscoelastic fluid, any polymer solution, any polymer stabilized suspension or emulsion or whatsoever, or polymer melt, will show this behavior more or less, meaning nothing else than at low characteristic speeds, your viscous behavior overcompensates the elastic behavior. Again, we talk time scales. You give your system, while you stress it, while you deform it, enough time to relax. Okay? The polymer chains, for instance, are able to flow around each other. You enable the system to dissipate the energy by viscous flow. The faster and faster you oscillate, okay, the less time you give your fluid for those relaxation mechanisms, okay, the more you freeze your sample in, the more you force it to behave more and more elastic. Okay, polymer segments cannot flow around each other anymore. You freeze in the three-dimensional network. More and more energy can be absorbed elastically, and at one point or another, which is very characteristic for your products, a lot of people use that in QC also, that test, the elastic response overcompensates the viscous response. Okay, and now just as a rule of thumb, this is exactly the point where the problems start. Okay, this is the point where die swell starts in your extruder. If you work at characteristic speeds above the crossover for your polymer melt, you will have die swell behavior. You might even run into shark skin already. Okay, this is the point where a shampoo, when it's being applied, will show the siphon effect. Okay, you squeeze shampoo out the bottle, you release the stress, everything is sucked into the bottle again. Okay, cheap products in hotels usually show that. This is the point where a shampoo again feels sticky after it's being applied by your customer, when the customer takes the hand off again. This is the point where a food product starts to behave to feel slimy. The mouth feeling goes down the drain. Okay, or a specific food product cannot be swallowed so nicely anymore. This is the point where the problems start. Okay, as a rule of thumb, keep that in mind. Okay, and this can be determined very, very quantitatively with a frequency suite. In that crossover point that again separates the more viscous domain or flow domain from the elastic domain, the phase angle, of course, is exactly 45 degrees. We are right in between purely viscous and purely elastic behavior. Especially when you talk about polymeric fluids, polymer solutions, no matter what kind of product you work in, as soon as you add polymer, okay, to stabilize it, to enhance the viscosity, to do whatever with it, you can, of course, custom tailor your viscoelastic response a lot by working with different polymers or different molecular weight distributions, for instance. As soon as you change the molecular weight of a given polymer, okay, you want to just thicken a shampoo, let's say, and you use carboxymethyl cellulose or methyl cellulose, something. You have the same polymer, higher molecular weight, means nothing else. At the same weight concentration means nothing else that you shift this crossover to lower frequencies. The higher the molecular weight of the polymer is, the more elastic it will behave. The longer the chain, the longer the rubber band, okay, when you think of that as a model, the more energy it can absorb elastically. The earlier you will see this transition. Okay. However, this is also true for the distribution. Okay, broad distributions usually bring down the moduli, okay, and usually also show a slightly earlier transition. Narrow distributions for one and the same polymer bring up the moduli in the crossover and usually shift them slightly to higher frequencies. Okay, so this is something that you really have to tinker around with to formulate the perfect product for a certain application. oscillation. For polymer solutions, of course, temperature has a severe influence. This is something we're going to talk about a little bit later on when we talk about time temperature superposition. The lower you choose the temperature, the more elastic your system will behave. Okay, when you cool your system down, you make it less and less easy for the system to relax, to flow, for segments to flow around each other. You make it more and more solid-like, okay, and vice versa. And concentration, of course, same effect. High concentration for one and the same polymer, higher moduli itself shifted to lower crossover frequencies, and vice versa. So this is really important. Keep that in mind. It's something you really can tinker around with. What you can also do, and I will talk about this very, very briefly, only because of time constraints here, oscillation is also the method of choice on the rheometer to look into temperature and time-dependent effects. Okay, you want to look at the curing, you want to look at phase transitions between solid-like and liquid-like behavior, you want to look into stability, how long is my fiber stable at a certain temperature, even under certain humidity conditions. Oscillation is the way to go. Okay. For tests like that, like a temperature sweep, for instance, you keep pretty much everything constant, deformation-wise, frequency-wise. All you do is you change the temperature, for instance. Okay, here we have the graphical depiction. We keep everything constant, strain, amplitude, as well as frequency. We just ramp up the temperature, for instance. And just as an example, when you measure a polymer with something like that, for instance, a purely amorphous polymer like polystyrene, your results will look like that. That at low enough temperatures, you will have no dependence in your G prime and G double prime. This is below the glass transition temperature. Okay, at higher temperatures, everything changes. Okay, your system softens. Your G prime goes down. Your G double prime goes through a max, which we then can call the glass transition temperature, for instance. Just as a tiny reminder, glass transition temperatures determined with a rheological approach or DMA approach, if you want to put it like that, because that can be done with solid clamps and DMTA type test on a rheometer, has a resolution of roughly 1 order of magnitude better than when you do with a DSC. Okay, this can be, of course, done with semi-crystalline polymers or cross-link polymers. I don't want to go into too much detail here because we run out of time already. You can look that up in the presentation that we hand out later on. Okay. Now, one important part about oscillation is also that you have the chance to expand the measuring regime. Okay. Again, let's take polymers as an example because it's the largest market for oscillation. When you look into polymers, polymer solutions, polymer melts, doesn't really matter. You usually want to see the whole picture. Okay. You want to see not just the flow regime, but you want to also monitor the elastic plateau. How long will it behave purely elastic before it goes into the glassy state? Okay, again, don't forget a polymer solution, a polymer melt will go through a dynamic glass transition. The higher you choose, when you choose the frequency, the speed high enough, your system will not be able to follow. Okay, and will behave as if it would become a solid, even if it's in a molten state, your polymer. Okay, and this is what we call dynamic glass transition. So you might want to measure this whole range. The problem now is that the rheometer doesn't let you. Okay, the rheometer tells you, no, my measuring range is limited due to two different reasons. You are limited to look at to the low frequency side just by measuring time, and I'm going to talk about this in a little bit more detail here in a second. And at high frequencies, you are limited due to inertial effects. Okay, again, we go to 100 Hertz, meaning nothing else. The rotor has to be accelerated 100 times per second in different directions. Okay, so inertia becomes very, very prominent here and gives you a lot of noise on your data. And you also have some eigenfrequenz problems in the rheometer itself, of course. So your measuring window is limited. However, for some materials, you can use a trick to expand this window. Oh, this is the slide I was talking about in terms of frequency ranges at lower frequencies. I mean, we all us producers, us and our competitors are always proud to say, yes, we can measure down to 10 to the minus 7 hertz or even 10 to the minus 8, which is all nice on paper, but always keep in mind that one oscillation at, for instance, 10 to the minus 7 hertz takes roughly 12 days. One oscillation cycle. Okay, to generate one valid data point, you need at least 3 oscillation cycles. That is 1 month. Okay, yes, we can do it if you have the time to wait for it. Okay, and again, on the high frequency limit, we have 100 hertz. What you can do now, however, is this trick that we call time temperature superposition. Okay, we use this mirror relationship that at high temperatures your system will behave like it would at low frequencies. Okay, high temperatures, it behaves more viscous, the same at low frequencies, and vice versa. At low temperatures, it behaves more elastic. Okay, at more elastic means higher characteristic speeds. Okay, so what we can do is we can do frequency tests in a very standard range, let's say from 10 to the minus 2 to 100 hertz. Okay, that's a test that's done in, let's say, 7 minutes. Okay, and then we just do the same test over and over and over again at different temperatures. And then afterwards we tell the software, and now shift them please. You can choose at which temperature you want to shift, and we can shift them on top of each other. Okay, this is what we call time temperature superposition. A lot of people, especially in the polymer industry, use it, but there's also other samples where you can apply this theory on. The only relevant information, or the only relevance from your product is that this relaxation mechanisms I was talking about in terms of different time scales when you apply different speeds have to have the same temperature dependence. There's tons of papers on that. If you need information on that, just let us know. We can provide you with that. So TTS is something that is done a lot. Okay, something that I don't even want to talk about today. That's a separate topic and a separate presentation. I think later on, also this year, we're going to talk about this slightly. Is that you now can actually extract molecular weight information from oscillatory data. Okay, remember the slide I showed you. Higher molecular weight means you shift the viscoelastic response to lower characteristic speeds. When you know the polymer that you work with, you can use the viscoelastic response and calculate molecular weight and molecular weight distributions from the viscoelastic data. It's fairly easy, and in the let's say the high polyolefin industry is used more than the standard GPC or whatever approaches to molecular weight nowadays. Okay, and of course this does not just account for the moduli, but it does also account for the viscosity. Okay, we also track the complex viscosity. I was talking about that earlier. Okay, over a very broad range of characteristic speeds now. Okay, and as I said earlier, this complex viscosity is one and the same thing as the steady shear viscosity according to the so-called Cox-Mertz rule, which is, I have to admit, a purely empirical rule. However, it works unless your system shows very strong energetic interactions. Okay, when you have a system that shows dilatant or shear thickening flow behavior, like a PVC plastisol, for instance, where you have shear-induced structure buildup, okay, happening only in the nonlinear deformation regime, you will not monitor this in oscillation. Other than that, the viscosity functions are one and the same. So many people, especially dealing with viscoelastic fluids, use oscillatory rheology exclusively nowadays for their rheological tests, and no steady shear tests anymore. Okay, with this I want to close. I hope this presentation was interesting for you and that you learned something from it. Thank you very much for your attention. I think we have a couple of minutes for questions here. I see a question from Carlos. If it is possible that the viscous regime is not observed in a frequency sweep. Yes, Carlos, that is possible. I mean, you have two answers to that. Either you have a gelled structure that does not show a viscous flow regime, okay, no matter how low you go in characteristic speed, or you have a system that has a transition between viscous and elastic flow behavior at very, very small speeds because it behaves extremely elastic, and then you would have to just further decrease the characteristic speed that you tested. Okay. Another question from Carlos: if G prime and del prime can cross again after the elastic regime? Usually not. I mean, this behavior I was showing you, the speed-dependent behavior after the elastic plateau, when you further increase the speed, you will go into this dynamic glass transition. However, in that glass transition, also your elastic component will always overcompensate the G double prime. So you should not have another crossover unless something happens to your sample. Okay, always keep in mind that your sample might show some time-dependent effects. Okay, that something happened to your sample, or that you, for some reason or another, did not work in the linear regime, but you measured in the non-linear viscoelastic regime, so that you actually destroy your sample when you do this test, and then you might have another crossover. Yes. What do we have here? There is a question from Anusha, that when she does creep tests for viscoelastic materials, the strain appears to be negative. That is something that should not be. I mean, you have to be careful that you reset the position before you do the test, but the sample should not pull back the rotor further than from where you started out at. That is something that should not happen, again, unless you use too high stresses that would maybe even introduce non-linearity in your fluid. But negative strains should not be observed there. Okay. There is another question from Rupa. If there's a specific geometry for the rheometer when doing oscillatory tests, this is, of course, it's not an easy question. All I can say is let's say it depends. I mean, when you work with polymer melts and structured fluids, you of course do not want to use cone and plate geometries. You usually want to use plate and plate geometries. Okay, in order not to destroy or not to stress the sample too much when you actually achieve the measuring gap. But again, we had a presentation last month. I also did that when I was talking about how to achieve good data for quality control, and my colleague Klaus also did a presentation on how you should prepare to get good results earlier in this year. I think that was in May. We have those presentations available as presentation PDF, or also as recorded versions, where we just talk about what you have to take into account, which kind of rotor should you use, what do you have to do before, and we can make this information available for you, of course, if you want to. Just let us know and we can distribute that. Okay. All right, thank you. That was all with the questions. Thank you very much again from my side. Thank you for your attention. I hope it was helpful for some of you. Always check back on our website if there's upcoming webinars that you might be interested in. As Klaus said earlier, this presentation has been recorded, and the link with the recorded version will be distributed to you together with the presentation as a PDF. For now, thank you again from my side. I hope we're going to meet again for another session, or maybe in person somewhere in the future. Have a great day. Bye-bye.